Hello, and welcome to the second part of Lecture 22. In this video, we're going to cover examples that highlight relativistic momentum, relativistic kinetic energy, and relative velocity in special relativity. It's a mouthful. All right, so I've chosen a few examples that I want to show solutions to because of their particular background and how they support the equations and the ideas. And of course, I'll be leaving some for further practice. All right, so let's take a look at example 1. This is a kind of the less of a actual particular example and more of just kind of a little proof here, but I thought it was very relevant. So I asked you to show that relativistic kinetic energy reduces to classical kinetic energy for V much, much less than C. All right, so let's show that. So relativistic kinetic energy has the following form. Here I've specifically given it the subscript of relative. Notice I didn't do that in the key equations because all of these equations for momentum and energy, right, all of them I guess, but also even the equations for relative velocity, they all reduce to the classical equations for V much less than C. So they all become the classical equation. So I don't really need to add a subscript to them because they really are true in all cases. It's just that we don't bother to use them for a velocity at, say, 1,000 meters per second, let alone 10 meters per second. So the least obvious one that reduces or simplifies to the classical version is this one, is the energy one. And this is really the one where we have to use the binomial expansion, okay? So that's kind of the reason that I mentioned the binomial expansion a minute ago. So anyway, so here's the expression for relativistic kinetic energy with its two terms, right? So this is its, kind of the total energy, in fact, and then minus the rest energy. So that's what relativistic kinetic energy is. It's total energy minus rest energy. Okay, so then I factor out the like term of mc squared, and then I go ahead and I rewrite the 1 over the square root of 1 minus v squared over c squared in this form, right? So I've turned the square root in the denominator into -1/2. That way I can clearly use the binomial approximation. All right, let's do it. And there it is. So when I use the binomial approximation, this whole thing here in the box becomes this in the box, okay? The 1 is still there, which means that once I use the approximation, those 1s cancel, okay? So then all that's left inside the parentheses is the 1/2 v squared over c squared. Our like term of mc squared is still in the front. So then I go ahead and show the multiplication, cancel out the speed of light squared, and there we have it. Classical kinetic energy, okay? So it better, right? Because that's the thing about having a complementary theory like special relativity. It explains something that was not explained before, but doesn't tell us that Newtonian mechanics is wrong. It just tells us the Newtonian mechanics only applies to slower velocities. And by slower, we mean like anything that's less than incredibly fast, okay? All right, so there we have it. It works. Big green checkpoint, okay? So hopefully that's interesting. Now, example 2, I'm going to leave for you. This is a pretty traditional relative velocity equation where the velocities are great enough to necessitate using the special relativity versions of relative velocity. Because here we have electrons that are moving at 70% the speed of light. They're moving away from each other, opposite directions. And then what is the speed of one electron as measured from the other, right? So how fast would one electron see the other one moving? Because of course, in classical mechanics, if you had two objects that were both moving away from each other at some velocity, in this case, 70% of c, well, what would happen is then, either one, say this one here, would observe the velocity of the other one moving away at 1.4 the velocity of c. Of course, that can't be the case. I mentioned in the key equations why that can't be the case and why the equation corrects for that. And so you're going to have to plug in the numbers and find out how fast each electron sees the other one moving away, because it's going to be less than c. It's going to be greater than 0.7 c, but it's going to be less than c. And so you're going to use these equations here, whichever one you want. Okay? So that's left for your practice. All right, so now on to example 3. This is one I wanted to show you. So an armada of spaceships that is 1 light year long as measured in its rest frame, okay, moves with speed 0.8c relative to a ground station in frame S. A messenger travels from the rear of the Armada to the front with a speed of 0.95 c relative to s as well. How long does the trip take? Measured in the rest frame of the messenger, in the rest frame of the Armada, and by an observer in the ground frame s. Okay, so we have 3 reference frames here. Since we have 3 reference frames, what type of problem this should appear to be, and of course this takes practice to kind of identify what type of problem we're talking about, is going to be a relative velocity in special relativity type of problem. Okay, so just like the one that I left for your practice, example 2, example 3 is that same type of problem. So it's got a bit more to it, right? More story and so on. So that's going to involve using, this idea here, right? Because we have 2 reference frames. We have the rest reference frame, we have the Armada reference frame, and then we have something that's moving relative to the rest reference frame, and that's going to be the messenger. Okay. So that's the rocket or whatever, right? That's the third object. Okay. So let's take a look at step 1. So we will call SM the frame of the messenger. So in SM, we want to find the velocity of the Armada. Okay, so how fast is the Armada moving relative to the messenger? Because remember, the Armada is moving at 80% the speed of light relative to a planet at rest. Okay, but that's not how fast the Armada would be moving relative to the messenger, because the messenger is traveling from from the rear to the front. So that means the messenger is moving in the same direction as the Armada, right? So if the Armada is moving this way, then the messenger is moving in that same direction, okay? But just faster. Okay, so then we'll plug in the velocity of the Armada relative to the rest reference frame. We'll plug in the velocity of the messenger relative to the rest reference frame. All right, so there we have it. That's just using our relative velocity in special relativity equation. So we get negative 0.625. Of course, it's negative because, this would be like if I asked, if you were in a car and you were passing another car on the freeway, and I asked you how fast is the car that you're passing moving relative to you, you get a negative number because it would appear to be moving backwards. Right? If you're just looking out the window, the car would appear to be drifting backwards. So of course, it's a negative velocity. Same thing here. The Armada is drifting backwards relative to the messenger at a speed of negative 0.625. Okay? So notice that. That's kind of interesting because that tells us that it's drifting backwards at a greater rate than you might think, right? Because the messenger is only moving, 0.15, only 15% faster relative to the speed of light. But yet the Armada is drifting backwards at 62.5% the speed of light. So so relative velocity equations don't always give us something slower than we expect. Okay? Okay, so then I want to find the length of the Armada in the reference frame of the messenger. So this problem involves both relative velocity and length contraction. Okay? And I could use time dilation as well, but I choose to use length contraction. So then I'm going to find the length of the Armada, all right, in the reference frame of the messenger, and I call that L1, and that's going to be the rest length divided by the gamma that I got for the messenger, okay? So the gamma that I have, I'm going to use for the relative velocity. So notice here, I take the rest length of the Armada in its own reference frame. So that I really, calling it the rest length is, so really, I should be calling it what's the term I'm looking for? It's just escaping my mind. Here, let's pull it up. All right, so there we go. So I want to call it the proper length. The term just wouldn't come. So this is really the proper length, right? Because that's the length measured in the reference frame of the Armada. So that's the length that's in that reference frame. In the reference frame of the Armada, that's the time that the length is at rest, right? Because in any other reference frame, the planet's reference frame or the messenger's reference frame, the Armada would be moving, so the length that they measure would not be the proper length. Okay, so this is the proper length, the 1 light year. Right, it's a very long Armada. This is, wild sci-fi stuff. And then I'm dividing by gamma. Well, dividing by gamma is the same as multiplying by multiplying by the square root of 1 minus v squared over c squared. Okay, so in this case, my v is just going to be 0.625c. Notice that I just wrote 0.625 because the c squared would cancel with the c squared in the denominator if you look at the definition of the Lorentz coefficient. Okay, so that's, and then the negative is going to go away because I'm squaring it. So then I get a length of 0.781. Okay, so what's going on here, right? So the whole idea here is I found a relative velocity between the messenger and the Armada. Then I use that relative velocity along with length and traction to find out how long does the Armada appear to the messenger. Of course, it would appear shorter, right? That's in any other reference frame other than the reference frame of the Armada will appear shorter. Okay, so relative to the messenger, the Armada is only 0.781 light years long. Okay, and the light year here is just length. Okay, not a time, obviously. Okay, it's the okay. All right, so good. All right, it's just the distance that light travels in 1 year. All right, so then I need to find t prime for the messenger. So t prime here is just going to represent how long the trip takes, okay, for the messenger. So then I would take the contracted length divided by v prime, and again, v prime is just the velocity of the Armada relative to the messenger. So I take the contracted length divided by the velocity between the two, the relative velocity of the Armada to the messenger, or okay? So 1.25 light years. Okay, all right, there we have it. It would take 1.25, I don't know why I said light years, 1.25 years for the messenger to go from one end of the Armada to the other. Okay, and again, that I was able to simply cancel out my units because a light year is how long it takes light to travel, or how far it takes light to travel in 1 year, and then c is just the speed of light. Okay, so then of course the units I'm going to get are going to be units of time, and they're going to be specifically years, not seconds, okay, or any other unit of time, so specifically years. All right, so 1.25 years for the messenger. Okay, let's continue on because now we want to say, well, how long will it take in the rest frame of the Armada? Should be the same time, right? Because that's all I'm saying is how long does the trip take? Well, of course not, okay? So call the reference frame of the Armada SA. Okay, so then I'm going to find the velocity of the messenger relative to the Armada. When I do that, I get 0.625, okay? And that's a good reality check because they should agree, okay? So that's just telling me how fast is the messenger moving relative to the Armada. Because before, this was how fast the Armada was moving relative to the messenger, backwards at 0.625. This is just how fast the messenger is moving relative to the Armada, forward, but same value, 0.625c. Okay? So now I'm going to take the time it takes for the messenger to move, as measured in the reference frame of the Armada, would be the proper length divided by the velocity, the relative velocity of the messenger relative to the Armada. So our denominator is the same, but our length is longer. It's 1 light year instead of 0.781 light years because there's no contraction in this case. It's just a proper length. And so then the Armada would measure a time of 1.6 years. Now, what do I mean by measure time? So let's say we've got people that are part of this Armada in the different places. So if I was at the front of this Armada, I'm the general of the Armada, okay? And the messenger leaves, right? They hop on their ship and they start flying forward, right, to go from the rear to the front. I'm going to have to wait for 1.6 years in my reference frame before the messenger gets to me, okay? However, the messenger would have only had to wait on board their ship 1.25 years. So biologically, they would have aged 1.25 years. I would have aged 1.6 years by the time that we met, okay? All right. So now part C, by an observer in the ground frame, okay? So now we want to find out how long does it take as measured from someone, stationed on the planet that happens to be maybe nearby. Our Armada is maybe passing through this system or something, okay? So L relative to S. Here I have S, that's the rest reference frame. Okay, so then I would take the proper length measured in the Armada's reference frame divided by gamma, okay? Gamma here is not going to be the relative velocity, so I don't have to worry about relative velocity for part C. I only have to worry about the velocity, at least not relative to two moving things. I only have to worry about the velocity of the Armada relative to rest, which we're told was 0.8. Okay, So then I get a contracted length of 0.6. Notice my contraction is larger. Well, of course it's larger because it's a greater velocity. You know, the Armada is moving faster relative to the planet at rest than it is to, you know, then the messenger is moving relative to it, or then it is moving relative to the messenger. Okay? Okay, so then I get 0.6. So now I'll use that along with the relative velocities to find out how long it takes. Okay, so then the time that a planet-based observer would measure for the time it took from the messenger to leave the end to get to the front would be the contracted length, as measured in their reference frame, and then the velocity. Okay, well, what velocity would they measure? Well, they would measure simply the difference between both velocities relative to them. Okay, so they would have the velocity of the messenger minus the velocity of the Armada. Okay, because from their point of view, in their reference frame, not even point of view, but absolutely true in their reference frame, the messenger is moving at a rate of 0.15 times the speed of light faster than the Armada itself. Okay, and so they get the longest time. They get 4 years. All right, so it would take. So they would measure 4 years. They would have to wait 4 years for essentially for the information to happen. So what does that mean? Well, let's say there's a signal, right? Let's say this is happening like really near the planet. So what's going to happen is as soon as the messenger gets there, they're going to convey their message to the general. Then the general's going to be, oh, okay, this is good to go. This is really important, right? And maybe they have to actually bring something in person. Maybe they bring a key or something, you know, so that would necessitate the reason they have to physically be there. You know, so the general then plugs in the key, and then that key is able to send out a message. That message is going to travel at the speed of light, and let's say this is all happening close enough to the planet's going to get that signal fairly quickly, okay? You know, within minutes or something. So that for the whole time from when they got a signal that a messenger is leaving to the time that they were told that the message, that the key was received, and so on, they would have to wait 4 years for that to happen. Okay, so it'd be 4 years later for them, where again it would be only 1.6 years later for the general at the head of the Armada, and only 1.25 years later for the messenger. They all have different amounts of time to wait. It's amazing, isn't it? Okay, so good example of, you know, this using both relative velocity and length contraction in a single problem, and just kind of following the steps there. I know there's quite a few steps, but if you can follow them and see where it goes, the pieces will come together. And really makes you think about how if you did have relativistic travel, you'd have a lot of logistics to take care of, right? You'd have a whole other set of complications in terms of how to manage things, this being kind of a case in point. Okay, so now example 4 I've chosen to show you because it's got a step in it that is very important because it's going to be in your post-quiz, the post-quiz that you're going to be taking next week. Okay, so this is the lecture that's going to help you understand this important step in the post-quiz. So example 4, an interstellar dust particle with a mass of 1.8 times 10 to the negative 9 kilograms experiences a force of 1.35 times 10 to the negative 6 newtons. If the force is parallel to the particle's velocity of 0.8 c, what is the particle's instantaneous momentum and acceleration? Okay, so I'm only going to do part A because I'm going to leave off part B. Let me do this. I keep getting notifications. I'm going to leave off part B for practice because part B is really identical. It's just different numbers. So no big difference there. But it'd be good practice maybe to do it blind. Make sure you can do the steps without referring to my solution. Now, the equation here is not one that shows up in your key equations because it's not in your book. I'm only giving it to you because you need it for the post quiz. So it's a little added content. Okay, but it's not particularly difficult. It's just Newton's second law in relativistic form. Okay. Now notice I say that it's parallel, and that's because if it's not parallel, if it's perpendicular, then there's actually a different equation, and this can be shown simply with calculus. But here we only care about the parallel one. I'll never ask you for the perpendicular components or anything in between. Okay, but here you just got this. Okay, at least not in this class. I do plan on doing it for Physics 38 because they were going to use the calculus. Okay. So step 1. Okay, so here we have a velocity of 0.8 c. So the first thing I'm going to do is find gamma. Now, I didn't do that for the previous problem, because even though gammas did come up, I had multiple gammas, right? I had different values, and so I didn't bother to do it, because I was going to have to do relative velocity anyway for parts A and parts B, and so it didn't quite make sense. But in any other problem where you don't have relative velocities, it always makes sense to do your gamma right away because you're going to be using that a lot. Okay, and that's definitely true of the post quiz. So here I find the gamma right out the gate, first step in the problem, 1.67. Okay, so my relativistic momentum was just going to be gamma 1.67 times m times v. Okay, and remember gamma is unitless; it's just a dimensionless coefficient. Okay, so then I go ahead and find relativistic momentum. All right, so there we go, 1.67 times m, and then times v, which is just 0.8 times the speed of light. Here I'm using the approximate version of the speed of light, 3 times 10 to the 8. All right, so then I have my momentum in Newton seconds, right? Not particularly large, but that's fine. It's a tiny, tiny particle, so that makes sense, right? Because it's such a small mass. Even though it's a very high velocity, it's a very small mass. Okay? So then it's simply a matter of finding the acceleration. Okay? So then this is now the only time that I'm using Newton's second law. So then I'm going to find, and then you're going to do this a lot in the post quiz. So then I take the force that's given to me. Okay, there's my small force, 1.35 times 10 to the negative 6 newtons, so 1.35 micronewtons. And then I divide it by gamma cubed, so 1.67 cubed times the mass of the particle, the dust particle. And there I have an acceleration of 154 meters per second squared. Okay, so it shouldn't be a surprise that Newton's second law isn't F equals ma anymore. Okay, because look, now it's F equals gamma cubed times ma. The gamma cubed, again, you can't guess where that's coming from unless you do the calculus. But again, it shouldn't be a surprise that it's not the same because momentum's not the same. And if you recall, I mentioned in passing, although I didn't make too big a deal out of it, that one way that relativistic momentum is sometimes justified is the idea of relativistic mass. Well, if there's this kind of hand wavy justification of relativistic mass, that should apply equally well to Newton's second law, that is F equals ma after all, right? It's got an m in it. And so that same effect of relativity is going to apply to mass times acceleration. Okay? And so, in other words, this is not the acceleration that you would get if you tried to use classical mechanics. It'd actually be interesting to find out what the deviation is between the two, but it'd be pretty significant at such a large velocity, so close to the speed of light. Okay? All right, so there you have it. That's how you do this problem. Okay? And I'll leave part B for you. Same approach, just different number. All right. So I'm not going to do, actually I'm going to do one example on this one. So I'm going to do example 5 because it mentions work and we haven't done that. So the work that must be done to increase the speed of an electron. Give you the mass of the electron from a speed of 0.9 c to 0.95 c. Okay, so how much work does that take? So the reason I'm showing you this example is I want to show you that the work kinetic energy theorem applies equally well to relativity, because as long as we use relativistic kinetic energy, we can still use that W equals delta K, right? W equals delta K is still true, okay? Okay, so here we have it, W equals delta K. So this is my K final minus my K initial, okay? Or KE final minus KE initial, okay? I'm calling K for kinetic energy. Okay, so that would actually just be gamma final minus gamma initial times mc squared. Oh, okay, cool. All right, so then I go ahead and just find the gamma. I don't show the work here, but if I just use the equation of gamma equals 1 minus the square root of 1 minus v squared over c squared, and both the v's are given as fractions of c, then it's just going to be the square root of 1 minus, or 1 over the square root of 1 minus 0.9 squared, and then the other will just be 1 over the square root of 1 minus 0.95 squared. Simply that. And it ends up being 3.2 and 2.3. Okay, and it also really shows you how gammas have a big effect, right? It's because here we only went up by 5% the speed of light, but we went from 2.3 to 3.2. Okay, if we went up another 3% to 0.98, then our gamma would jump even more. And then times m times speed of light squared. All right, so there we have it. It would take 7.45 times 10 to 11 joules. Whoa, that's a lot of energy, right? That is a huge, huge amount of energy. Okay, let's see. Oh, it should be negative 11. Whoops. Right, because if I'm looking at my equations here, because I have 16. Oh yeah, I'm like, that can't be right. First I was like, oh, I was going to make a point about how big it was, but then I remembered other problems where it's still in some. The reason is because it's such a small particle, right? Electrons are really, really small, and so here, if you think about it, this 10 to the 8 would be 10 to the 16, and then negative 31 plus 16 gives us that should give us our 11, right? If we deal with the other factors. Yeah, because we think 16, basically like 15, and then we have a multiplying by, by 10, and so on. So it should give us negative 11. So I'll fix that before I upload it. Okay. So last example I want to show you is this one here. An extremely energetic proton in the cosmic rays surrounding Earth has a kinetic energy of 3.0 times 10 to the 17 electron volts. Okay, so we'll go ahead and convert those electron volts over to joules. Okay, and that's going to be something we're going to be seeing a lot of. So again, this is kind of a foreshadowing things to come. We're using a lot of electron volts, basically up until the final at this point. What are the protons' Lorentz factor, gamma? Okay, so here I explicitly ask you for it, and again, it's always a good habit to solve for it first. And the speed v in the Earth's frame, so the rest reference frame. Part B, how long does it take this proton to travel across the Milky Way in the time of Earth's reference frame? And then how long does this trip take in the proton's reference frame? So a little bit of time dilation here. Okay, so let's do part A. Okay, so relativistic kinetic energy. Probably getting used to seeing that by now, I hope. All right, so first of all, I'm going to write out the energy that we're given, right? So we're told that this proton has kinetic energy of 3 times 10 to the 17 electron volts. So here I'm just converting that to joules. The conversion factor between joules and electron volts is 1.602 times 10 to the negative 19. That's just the, because remember, that's the voltage of a, or really it's the fundamental charge. It's the charge of a single electron. That's the way to think of that. Okay, so there, we've converted it over. Okay, so then I'm just going to solve for gamma. That's all. I've just isolated gamma from the expression above. You can see all the numbers there. And so here we get a huge gamma. Why is that? Right? I mean, this is way bigger. Our gammas so far have usually been like just between 1 and 10, haven't they? Right? I mean, we maybe like, I'm trying to think if I know I have some examples where I show gammas of like, 25 or something, because this proton is traveling very close to the speed of light. In fact, it's very difficult, even with my TA89, I can't calculate how close it is to the speed of light, because it's basically going like 99.999 and then another like 8, let's see, another, well, if it's 10 to the, I mean, yeah, that's the thing, we're going to square it, so 16, so basically it'd be like 99.99 and then 16 nines % the speed of light. So it's so close to the speed of light that even when we use the value of the speed of light, the one that has all the significant figures, it's still going to show up as the same value. Okay. Now, but then why did I choose that? Why did I choose for it to travel so close to the speed of light? Well, because I just gave it a huge amount of energy, right? Because I told you that I could give the proton any amount of energy and it'll never actually get there. It'll always get asymptotically closer to the speed of light. It'll never truly reach there because it takes an infinite amount of energy to take a proton with mass to the speed of light. Right? So this is a huge amount of energy. Well, actually not that much energy, right? If you look at it, but in terms of joules at least. But it got it very close to the speed of light, but never actually there. Okay, but let's not lose sight of what we're asked for, right? We're asked for how far is it going, right? Well, let's see. Okay, so here we'll go ahead and work it out. So we have the velocity. So then if I go ahead and solve for the velocity, and here this is just using the definition of gamma. Okay, because gamma is equal to 1 over the square root of 1 minus, right, this expression here. And so then if I start to solve for gamma, or excuse me, I start to solve for v, maybe the first thing I should do is take the reciprocal of both sides and square both sides. That's what I've done here. And then I just go ahead and isolate v, okay? And then I do that by, you can see, taking the square root of both sides to get v by itself. Since c was squared, it ends up being outside of the square root. And so when you actually plug this in, if you were to plug in a gamma here, you would get that this expression is so close to 1 that your calculator will tell you that it's just traveling at c, really, no matter what you define c as. Okay, we know it's not actually traveling at c, but it's traveling darn close to it. Okay, so that was kind of our answer for part A, right? Okay, all right, okay, it's going that fast, great. Nearly the speed of light. So in Earth's reference frame then, since the proton is going nearly the speed of light, and it wants to cross the entire Milky Way, which is 9.8 times 10 to the 4 light years, well, then it would simply take 9.8 times 10 to the 4 years, right? Because that is the size of our galaxy, by the way. Their galaxy is about 10,000 light years across, okay? Excuse me, 100,000, right? Because it's 10 times 10 to the 4. So it's about 100,000 light years is the diameter, about a 50,000 radius, but 100,000 light year diameter for the Milky Way. So if something's traveling basically at the speed of light, then in our reference frame, we would measure a time for it to travel of about 100,000 years. Okay, so that's how fast our energetic proton is going. But what about the proton? How long would it take it? Okay, so for the energetic proton, time is going to be the time that Earth measured divided by gamma. Oh, wow. Now we're actually going to use that big gamma and really do something with it. Because here it just basically gave us something that was approximately equal to 1. It kind of seemed useless. But here it will give us a meaningful value, because we're going to be dividing by something that 10 to the 8, but we're going to be dividing by a big number, especially in seconds. Okay, so let's do that. Okay, so here I take the 9.8 times 10 to the 4 years, so the 100,000 years, and then I convert it over to seconds. So I get my almost 100,000 years, 365 days in a year, 24 hours in a day, 60 minutes. Okay, so I'm actually not going to convert it to seconds. I'll leave it in minutes. Okay, and then I'll divide by my gamma, my Lorentz factor, 161 minutes. Wow. So for an extremely energetic proton, for something that was given that much energy and is that small, because protons, of course, are tiny particles, then it would measure a time, right? If the proton was conscious, it would only have to wait less than 3 hours to travel across the Milky Way, right? That's time dilation for you. And one thing I haven't mentioned, or at least don't remember mentioning too much, is that what does this mean for time dilation for something that is traveling at the speed of light? Well, then no time passes. So photons, the only or other, being massless can, and other massless particles could also travel at the speed of light, but photons being the most well-known massless particle, traveling at the speed of light, they would measure no time passage. Okay? And that really begs the question, what does that mean? What does it mean for a photon to have that time does not pass for a photon? Okay? Well, leave that the discussion for another day. But for things that are traveling really close to the speed of light, very little time passes. Very, very little time. Okay? And you might think of it, like, doesn't this seem like, but it traveled light years, but less time passed than the number of light years. Does that mean it's traveling faster than the speed of light? No, it's just because it's about reference frames. Okay? It's about reference frames. So, that's pretty remarkable. When you're traveling so close to the speed of light, so little time actually passes. Okay. So good. I hope this final exploration into some examples of the consequences of special relativity has been interesting and has helped you be in a position where you can solve these problems as well. Okay? Well, thank you for